I mentioned in the course introduction that to understand how tissues work, we need to look at lower levels of organization. In particular, how do cells work and how do molecules work? And so this mini lecture is focused on the molecules. And in particular, we want to understand what drives the motion of molecules. So these are the four tissues that we're talking about. And we've covered connective tissue. I'm not going to really talk about connective tissue, at least with a dedicated lecture anymore. As we move forward, we're going to focus on epithelial tissue, nervous tissue, and muscle tissue. And these three tissue types are all about membranes. And we're going to talk a lot about how molecules traverse those membranes and how these different types of tissue control the motion of molecules across membranes. So membrane dynamics are fundamental to understanding how these three types of tissues work. So the question for this mini lecture that we'll address is, how are molecules and ions moved across a membrane? What governs the motion of molecules? And there's three driving forces that we're going to consider. So the first is chemical diffusion. So you've got molecules in solution. And first we'll consider uncharged molecules. And let's just think about simple chemical diffusion. And for that, we're going to look at this movie here, which is just particles that are nothing special except for the fact that they're really tiny, okay, 88 nanometer diameter particles. And let's just look at how they move, okay? It's this frenetic thermal random motion that we can exhibit just by looking at these small particles under a microscope. Now, the speed of the motion of these particles depends on a variety of factors. They depend on the temperature, the mass of the particle, and then whether or not they have any interactions, molecular interactions with the solution, the water that is dissolved in, or other neighboring particles. Now, see if you can follow one individual particle as it's moving around. And if so, I defy you to predict which way that particle moves in, because its motion is random. Okay, at any particular moment, the particle that you might be tracking could change course, change direction, go backwards from the direction that it came from. Its motion is random. So it is true that for single particles in solution, they have no directionality. You can contrast that with the properties of a whole population of particles in solution. And so schematically, I've drawn that here. Just imagine there's lots of little white particles in a dark expanse of some liquid, and those particles are in solution. Over time, the way that population of particles looks is the margins of this population expand. So if you look at the margins, there is directionality, even though individual particles have no destiny. They're not directed in any particular way. Also note that the center of the population hasn't gone anywhere. So on average, the population of particles doesn't move. The center moves nowhere, but the edges are expanding towards lower concentration over time. So let's think about that a little bit more carefully. So we're going to look at that population of particles, and let's draw a line through the center like that. And then let's make a plot of the density of particles at each position along that line. And it would look something like this, something like a normal distribution with a peak of high concentration right at the center of the population. And at this initial time, we'll call time 1, the particles are pretty narrowly distributed. And as we play the animation, we see that over time, the margins expand, and the number of particles is the same. So if we look at that expansion over time, it would look something like this. So the density at the center decreases. So right there, we see a reduction there, but its position along the x-axis, which is the position along the line, doesn't go anywhere. okay? It still has a mean position at the same point in space. And as you continue through time, you see this flattening of the distribution. And note also the margins of that distribution. So here we can see that initially at time 1, there were no particles in these large distances from the center, but over time we see that the margin moves. So we have that motion of the edges, and we can say that the rate of edge expansion is proportional to the concentration gradient. Okay, so you have a more rapid expansion towards the margins when the concentration is greater. Now let's consider how the particles move as a function of time. Let's just say we have this bolus of particles in solution, and let's track how long it takes for particles to reach some distance. Okay, so what we have here is how long it takes for those particles to move. Let's just imagine it's some of the particles of the edge, or we could be tracking the edge itself. Let's just say we see this expansion of the edge. And what we have here is how long it takes for that edge to move over some distance. Okay, so that's the distance on the x-axis. And this function is time being proportional to distance squared. Now, if we take some physiologically relevant scales, let's just say at the membrane scale of a cell, then this margin of the population of particles is going to diffuse 20 nanometers in about 1 millisecond, or 1/1000th of a second. All right, that's pretty quick. 1 millisecond is fast. And so what we can see is that diffusion on that scale, this is sort of a subcellular scale, it's quite rapid, it's quite effective. We don't need any bulk flow such as is provided by the circulatory system in order for these molecules to move. So if it's a molecule, say glucose, that's being absorbed by an epithelial cell, or maybe it's a calcium ion, and the exact rates are going to differ depending on the molecular weight of the molecule, but both would diffuse rather rapidly across the cellular membrane. Now let's move at a greater distance, let's just say 1 millimeter, and we can see that that margin is going to take about 1.5 minutes, okay? That's pretty slow for physiology. Okay, if, say, these are dissolved oxygen molecules, there's a lot of metabolism that is achieved in 1.5 minutes. So that's not so great already. Already at 1 millimeter, we can see that diffusion is not a very rapid means of transporting molecules. And now let's consider the distance between, let's say, your lungs and your fingertips, or about 1 meter. We can see that if we relied purely on molecular diffusion to transport the oxygen that we inspire to reach the cells in our fingertips, we'd have to wait 3 years. Okay, so chemical diffusion is pretty poor at those spatial scales. 3 years is, I mean, you'd be dead by that time. So what we can see here is that although molecular diffusion is really fast at small scales, it's really slow at large scale. This is all just because the distance squared approximates the time that it takes for the motion of these molecules. All right, so most of our concern with regards to chemical diffusion has to do with the transport of molecules across a membrane. So for that, let's perform a virtual experiment. And that is one where we have a U-shaped tube. So this is just a piece of glass with a bend in it, and it's open at the top here. So we can add substances, and there's no resistance to the water column changing in its height. And on the right-hand side, we have molecules in solution. Okay, those are known as a solute, which is just a dissolved substance. And in between the left and right sides of this tube, we're going to add a semi-permeable membrane. So some things can get across that membrane. In this case, we're going to make it permeable just to the solute itself. And that's because we're interested in chemical diffusion of that solute across the membrane. And we can see the concentration is much greater on the right-hand side than the left-hand side. I just told you that the concentration gradient through space is an important factor in determining the rate of diffusion. And that's true across membranes too, but here it's the difference in concentration between one side of the membrane and the other. So that's the direction of chemical diffusion, or the net direction of chemical diffusion, and the rate at which the molecules traverse that membrane is going to be proportional to properties of the membrane. Okay, so this is the rate of diffusion. This is moles per unit time, so just think of the number of molecules over time. It's going to be proportional, and we use this alpha symbol to denote proportionality. It's proportional to what? Well, I just told you it's proportional to the difference in concentration across the membrane. All right, so we got that. Let's think about that. What else ought to matter about the membrane? Well, of course, if this is a homogeneous membrane and you were to make it thicker out of the same material, then that would tend to slow down diffusion, right? Okay, so thickness matters. And I mentioned earlier how exchange epithelial cells are very thin to allow for chemical diffusion. Here we see why, okay? The thinner the cell, the more rapid the molecular flux you're going to have across those cells. What else ought to matter? Well, what about the ability of the molecule to move through any thickness of membrane? Okay, that's known as the permeability. All right, and the permeability depends on the lipid solubility. This is for cellular membranes. Okay, because they have a phospholipid bilayer. And so if you have a molecule with higher lipid solubility, it's going to be more permeable. But if the molecule is bigger, then it's going to be less permeability. Okay, so there's other factors that affect permeability too, but this is the two that we want to emphasize here. Permeability matters with respect to lipid solubility and molecular size. What else? Well, of course, if you have a larger area to traverse across, then you're going to have more molecules go across that membrane. And so, of course, area matters as well. Okay, so this is a pretty intuitive concept that the rate of chemical diffusion depends on the concentration difference, the permeability area, and it's adversely affected by the thickness of the membrane. All right, all of these factors together are known as Fick's law. Okay, so Fick's law of chemical diffusion is what we want to use if we're interested in how quickly molecules move across a membrane. All right, so that's the first driving force, chemical diffusion. Fick's law tells us how chemical diffusion works across membranes. Next up is water. And in particular, we're interested in osmosis. So we have this funny word colloid in front of osmotic pressure. Let's think about that. So we're going to return to our little thought experiment here. Again, we have a semi-permeable membrane, but in this case, our membrane is not permeable to the substance in solution on the right-hand side, but it's permeable to water. Now, osmosis and the osmotic pressure is going to cause water to move towards the side of the tube that has higher concentration of the solute. So osmosis favors diffusion of water towards higher solute concentration. Okay, and as a consequence of that, you're going to have water moving towards the right and increasing the height of the column. And this is exactly the way it would look if we were to perform this experiment. We have this high water, head of water here compared to over there. And this is a case where osmotic pressure, it is an actual physical pressure, counteracts the weight of the water, and that difference in height we could use to quantify exactly what that pressure is. Now, in the case of blood and other liquid solutions that are in your body, you'll have a mixture of large molecules and small molecules. Okay, so we're going to make this a little bit more realistic, where the large molecules are proteins in solution, much like you have in the plasma of your blood. And it is common for semi-permeable membranes in the body to not allow those proteins to traverse the membrane, okay, because they're big. So this membrane does not allow the proteins to diffuse across it. However, it is common that small molecules can diffuse across a chemical membrane. So that's what we have here. We're allowing some of those small molecules, imagine ions, for example, diffusing down their chemical concentration gradient. So, because the large proteins remain on the right-hand side, even though we have a diffusion of small molecules moving potentially in both directions, but the net motion would be down the chemical concentration gradient. As a consequence of this, we're going to have a net concentration difference, where because of the semi-permeable membrane providing a barrier to proteins, we have a higher solute concentration on the right. Okay? And as a consequence of that, we're going to have more water drawn towards the right. The osmotic pressure will favor the water moving towards the right. And that is what we mean by colloid osmotic pressure. It's osmosis from a protein gradient. And in the body, that is such a common situation that we use that term all the time. Colloid osmotic pressure is what drives water towards the large proteins and therefore solutions of high solute concentration. Okay, so that's the second driving force. So in addition to chemical diffusion, we have this colloid osmotic pressure. Now, the third and final driving force that I want to tell you about are what occurs when you have molecules with a charge. Because charged molecules or ions, in addition to operating or being governed by chemical diffusion, now the charge comes in and plays a role in the motion of those particles. And that is because charged particles operate according to the electromotive force. That is, if there are similar charges, they are repelled from each other, and opposite charges will attract. All right, so let's look at the electromotive force in action. And here we have a slightly more realistic mixture of substances in solution, both inside on the right and outside of a cell on the left. And outside the cell, it's common to have a high concentration of sodium. We're showing the positively charged ions in red and the negatives in green. And potassium also has a positive charge, and it's in much greater concentration in the interior of cells. Now, this cellular membrane is permeable to potassium. And it is common that membranes are permeable to a particular type of ion. We'll explain later how that's possible. In this case, our membrane is indeed permeable to potassium. So potassium is free to move down its chemical concentration gradient, which favors the potassium leaving the cell. On the other hand, we can see that there are those positive sodium charges, and here we have more sodium than we do chloride. So there's a net positive charge of sodium on the outside of the cell. Whereas in the interior of the cell, we have those negatively charged proteins, which tend to, because of the electromotive force that we see in the bottom left-hand corner of the slide, the negative proteins tend to attract the potassium. Of course, the chlorides attract potassium as well. But the electromotive force will tend to favor potassium staying in the interior because we have a net positive charge on the exterior of the cell in this case. So what we see is that chemical diffusion favors potassium moving towards the left, whereas the electromotive force is favoring that motion towards the right. And this is not unusual, where we have chemical diffusion and the electromotive force acting in opposition to one another. Now, as a consequence, we'll see that there are some potassium now outside the cell. Okay, we got a potassium there and a potassium there. So here, the chemical diffusion is slightly more influential than the electromotive force on where those potassiums are going to end up. Okay, so we have a low concentration of potassium. It would be much greater if not for the electromotive force. Okay, so both diffusion and the electromotive force act on ions. And the final concentrations are determined by permeability of the membrane and these electrochemical gradients. Okay, so we use that term electrochemical when we're concerned both with chemical diffusion as well as the electromotive force. Okay, so that concludes the third type of driving force. So we can see the chemical diffusion, colloidal osmotic pressure, and the electromotive force are all important in governing the motion of molecules.